Hello everybody, welcome back to another Gregorius Maths video. Today I'll be doing number theory 1.4 and this will be an improvised session. I'll be proving the Weierstrass definition of gamma of S, which you'll have to watch till the end to find out what it actually is, okay? But I will give you a preview. It is written into it has a product in it. So I'll write gamma of S as a product. So this equals the product from, already I'm messing it up, 1 over S times, and in fact I'll write everything in terms of limits because that's probably easier to work with, times the limit as n goes to infinity of the product from k equals 1 to n of 1 plus 1 over k to the power of s times 1 plus s over k to the power of negative 1. Okay? And I'm pretty sure that this will evaluate to n to the power of s. So let's hope that I'm right about that. So this equals 1 over s times the limit as n goes to infinity of n to the power of s. Yeah, I think that should evaluate to n to the power of s. Times the product from k equals 1 to n of 1 plus s over k to the power of negative 1. Okay? And now, it's always helpful to write something in terms of e, especially when we have exponents and exponentials and stuff. This equals 1. I don't even know if it'll do me any good, but I can probably guarantee you that this will do me good. Just writing it as e to the natural log. By log, I do mean natural log. It's just that the ln and the n will be confusing. So of n to the power of s times the product from k equals 1 to n of 1 plus s over k. Okay? And now this equals, well, okay, in fact I should probably introduce the Euler-Mascheroni constant, which is widely known in the YouTube maths community as the Euler-Macaroni constant. But regardless of what it's called, it's definitely equal to the limit as n goes to infinity of the nth harmonic number times the natural log of n. Okay? And what this nth harmonic number means is, so the harmonic series is 1 plus a half plus a third plus a quarter plus a fifth, all the way up to infinity. And it might surprise you, it might not, that sum actually equals infinity. And this natural log, well, of course, the natural log of infinity is infinity. That's not surprising at all. But this part here, the harmonic series and the natural log, they grow similarly, similarly slowly. Okay, they both grow slowly. So Euler thought, what would happen if I subtracted them? Actually, you get approximately 0.577. Okay? So that's what the Euler-Macaroni constant is. Euler-Macaroni constant is. Okay? So the nth harmonic number is 1 plus a half plus a third plus a quarter plus a fifth, all the way up to plus 1 over n. Okay? So, because I know what the end result will be, I'm actually going to write it out like this, times the limit as n goes to infinity of e to the negative nth harmonic number times s. I know what the end result will be, and I'm pretty sure, this is an improvised session, but I'm pretty sure that this will pay off. plus the natural log of n times s, okay? We can just bring this s down because it's something to the power of a to the power of b. Using the natural log property, we can bring this down. But to cancel out this nth harmonic number times s, we have to write times e to the power of, not pi, but the nth harmonic times s. And then, of course, times the product from k equals 1 to n of 1 plus s over k to the power of negative 1. Okay? Again, I can almost guarantee that writing this as an infinite sum, or even better, as an infinite product, will do us good. So let's write this out. 1 over s times the limit as n goes to infinity of e to the negative nth harmonic number times s plus the natural log of n times s times the exponential function. Yes, this will be a lot neater writing as an exponential function. The exponential function of s times the sum from k equals 1 to n of 1 over k, just by the definition of the nth harmonic number. And then again times the product from k equals 1 to n of 1 plus s over k to the power of negative 1. Okay, the brackets have fricked me up, but just pretend that there's enough brackets and that you can see the negative 1 in the exponent. Okay? And actually, now that I think about it, this was actually a really good move, because now I'll write the equal sign here, 1 over s times the limit as n goes to infinity of e to the negative nth harmonic number times s plus the natural log of n times s times, and this is just a product of all of the exponential functions. So this is just, okay, so this e to the power of something, right? So this is equal to, this same as saying the product of all the, okay. So this is e to the power of a sum, right? So it's e times, so, okay, so if we have b to the power of a times b to the power of c, this equals b to the power of a plus c, right? So if we have a sum here in the exponent, this is just the product of all b times this sum, okay? Hopefully you can see what I'm saying when I write it out. Times the product from n equals 1 to infinity of the of e to the power of s over k, or just to say, stay consistent with my notation for one line at least, the exponential function of s over k times the product from k equals 1 to n of 1 plus s over k to the power of negative 1. Okay? And now we can combine the two products. I think I just had a brainwave. We can break this. I think we can make this two limits. Yeah, okay. So the first limit is e to the power of limit as n goes to infinity of negative nth harmonic number times s minus the natural log of n times s. Okay, because when you distribute the minus, you just get that. Times times the product, times another limit. Hold up. Times another limit as n goes to infinity of the product from k equals 1 to n of, we can combine these two together by just multiplying that and that. So 1 plus s over k to the power of negative 1 times e to the power of s over k. Okay? And now this is the precise definition of negative Euler macaroni constant. So this equals 1 over s times e to the power of negative... Oh yes, my brainwave worked. Because we've got s here and here, we get Euler macaroni constant times s. This would have been so bad if we just didn't have this s here. Because then this whole thing wouldn't have been multiplied by s. Whew, okay, because we can factor out an s easily. Yes, yes. I'm so happy. Times the product from k equals 1 to infinity. Now we're just plugging in infinity. Of 1 plus s over k to the power of negative 1 times e to the s over k. And now, taking the reciprocal, we clean up most of the negative exponents and leaves us with our final result. This implies that 1 over gamma of s equals, taking the reciprocal of this is s, taking the reciprocal of this is e to the positive Euler macaroni constant times s, times the product from k equals 1 to infinity of 1 plus s over k, because the reciprocal of this, that negative 1 becomes positive, but then times e to the negative s over k. And now we're done. Okay? And if this does not spark joy, then I don't know what does, because just, oh my god, it's so nice. Whew. It's one of my favourite definitions or theorems or whatever you want to call it, but oh so good. Oh, so happy. Okay. I'll just have this on my whiteboard as I sleep. Next time in bed I can just look up and see this. And I'll sleep soundly. And hopefully you will too. Good night.